Good day and welcome to Big Bad Tech. I'm your instructor Jim Pytel, and today's topic of discussion is transformers. Our objective is to examine the transformer, an electrical device used to step up or step down AC voltage. We'll examine how the turns ratio between the primary and secondary windings of an ideal transformer affect voltage and current, reflected impedance, and power transfer. This lecture operates under the presumption the viewer has more than a passing familiarity with AC power calculation, as illustrated in the AC Power and AC Power Examples lectures, both available at the Big Bad Tech channel. If you haven't watched these lectures yet, or only dimly recall their contents, please take the time to do so now. Let it be known up front, this lecture is not about the comic book, the television series, nor the truly awful movie franchise based on the popular Transformer series of toys from the dark ages of culture, the 1980s, but rather one of the most useful electrical devices ever invented, also of the same name. Without overstating their importance, transformers are absolutely essential to modern society and make it possible to not only transmit electrical power over vast distances, but also power a range of industrial devices using standardized distribution voltages. Transformers have had a profound impact on the way our society makes use of electrical power. Any individual knowledgeable about the function and construction of transformers can assure you that there is indeed more than meets the eye. A transformer is a device composed of no moving parts used to step up or step down, or if you want to think of it this way, transform voltage. A transformer does so through the process of electromagnetic induction. We'll examine electromagnetic induction in greater detail in later lectures. However, consider a brief summary of the process. Note all diagrams use the perspective of a conventional current. First, you should understand that electricity, movement, and magnetism are a related phenomenon. As current moves through space, it creates a circular magnetic field around it, where the direction of current influences the magnetic field polarity, and the strength of the magnetic field is proportional to the intensity of the current. In summary, when conventional current travels in one direction, the magnetic field will have a given polarity. If current swaps direction, so will the magnetic field polarity. Additionally, more current means a larger magnetic field, and less current means a smaller magnetic field. Given sinusoidal AC voltage continuously changes magnitude and polarity, it inherently contains a changing magnetic field. The electromagnetic induction process itself demonstrates that a voltage differential will be induced across the terminals of a wire loop placed inside a changing magnetic field, where this induced voltage differential is proportional to the rate of change of the magnetic field and the number of turns in the wire loop. In summary, the slower the magnetic field changes and the less loops in this slowly changing magnetic field, the lower the induced voltage. In contrast, the faster the magnetic field changes and the more loops in this rapidly changing magnetic field, the higher the induced voltage. If our loop of wire formed an electrical circuit that included a load, the induced voltage at the terminals of the loop would allow current to flow. This, at its core, is the basis of electrical power generation. Consider the rotor of a turbine, physically moved by water, wind, or expanding steam, where the rotor can essentially be modeled as a stick with a magnet on it, moving in close proximity to the windings on the stator. If the magnet is turned sufficiently rapidly, a large voltage will be induced across the stationary winding with a large number of turns. This same electromagnetic induction phenomenon also forms the basis of the transformer. However, instead of using a physically moving rotor to create a changing magnetic field, one uses another coil of wire in close proximity. The input of the transformer is sometimes called the line or primary side, and the output, the one containing the electrical load, is sometimes called the load or the secondary side. You'll note the basic schematic symbol of a transformer contains two windings or coils in close proximity to one another, directly hinting at its internal construction. Alternating current flowing in the primary coil would create a changing magnetic field. The secondary winding in close proximity to the primary experiences the same changing magnetic field, and via the process of electromagnetic induction, a voltage differential will be developed across the terminals of the secondary winding. Given induced voltage is proportional to the rate of change of the magnetic field, and importantly the number of loops inside the winding, an easy means of changing or transforming output voltage at the secondary is to simply vary the proportion of coils on the secondary with respect to the number of coils on the primary. If the secondary winding contains more turns with respect to the primary winding, a larger output voltage will be developed, and the transformer can be considered a step-up transformer in that the output voltage at the secondary will be higher than the input voltage at the primary. Similarly, if the secondary winding contains less turns with respect to the primary winding, a smaller voltage will be developed, and the transformer can be considered a step-down transformer, in that the output voltage at the secondary will be lower than the input voltage at the primary. In summary, the ratio of the number of turns between the primary and secondary determines the function of the transformer. Before examining this transformative relationship in greater detail, allow me to comment on the degree of coupling between the primary and secondary windings. While it should be obvious that the current flowing in the primary winding magnetically couples the secondary winding to the primary winding, it's also interesting to note that any current flowing in the secondary winding would also magnetically couple the primary winding to the secondary winding. This means that the source and primary winding can in effect see the load on the secondary side of the transformer, despite there being no direct physical nor electrical connection. In fact, the only connection shared by these two windings is wholly magnetic in nature. Can you now dig this on every level that I do? In addition to all the wondrous properties we are about to discuss, the core function of a transformer, if you want to think of it this way, is to transmit electrical power through free space. Put this in your pipe and smoke it. This transmission of power through free space is, however, not without its limits. It is for this reason that transformers ordinarily use an iron core, symbolized as a double bar between the primary and secondary windings. The iron core is substantially more magnetically permeable than air, up to 5,000 times for pure iron. This means that an iron core transformer is far more effective at concentrating the changing magnetic field linking the two windings. Although construction differences vary from manufacturer to manufacturer in use, a general diagram of an iron core transformer looks something like this. Imagine a ring-like structure of iron around which is wrapped the insulated coils of the primary and secondary windings. Any magnetic field generated by the two windings, rather than wandering off and getting into trouble, is instead confined to the iron core, thereby ensuring the two windings remain firmly magnetically coupled. I'll come back to correct this simplified diagram in a later lecture examining losses in non-ideal transformers. Before moving on, let me remind you that transformers necessitate AC voltage, something that cyclically varies both magnitude and polarity to function, since a changing magnetic field is a property essential to the induction process. DC, in contrast, is characterized by a steady-state value of a fixed polarity, meaning DC does not innately carry a changing magnetic field, meaning it cannot be readily transformed. It's for this reason AC has been adopted as the nearly universal standard for power generation and transmission. Additionally, note that since the voltage generated during the induction process is proportional to the rate of change of the magnetic field, high-frequency sinusoidal voltage can dramatically alter the performance of a transformer. We'll explore transformer ratings and high-frequency effects in later lectures. Moving on. As mentioned, the principal means the transformer uses to step up or step down voltage is to vary the proportion of turns on the primary and secondary windings. This relationship is called the turns ratio, and is customarily expressed as the ratio of the number of turns in the primary winding for the corresponding number of turns in the secondary winding. Given voltage is proportional to the rate of change of the magnetic flux and the number of turns, it can be said that the turns ratio between the primary and secondary is directly proportional to the voltage ratio between primary and secondary. Expressed more succinctly, the number of turns in the primary over the number of turns on the secondary equals the input voltage at the primary over the output voltage at the secondary. NP over NS equals EP over ES. By increasing the number of turns on the secondary with respect to the number of windings in the primary, a larger voltage will be developed across the secondary, and the transformer can be considered a step-up transformer, and that output voltage at the secondary will be higher than the input voltage at the primary. Similarly, by decreasing the number of turns in the secondary with respect to the number of windings in the primary, a smaller voltage will be developed across the secondary, and the transformer can be considered a step-down transformer, and that the output voltage at the secondary will be lower than the input voltage at the primary. Consider the following example. If a transformer primary winding contained 300 turns, and the secondary winding contained only 60 turns, we could say the turns ratio is 300 over 60, or just as easily 5:1. Given the larger number of turns in the primary and the smaller number of turns in the secondary, we can expect this transformer to function as a 5:1 step-down transformer, and that we'd expect our output voltage to be 1/5 of the input voltage. If 120 volts was applied to the primary coil of this 5:1 step-down transformer, a simple algebraic rearrangement of our equation demonstrates that 24 volts would be developed across the secondary winding. As we'd expect, the output voltage is 1/5 of the input voltage for a 5:1 step-down transformer. It makes sense. A practical application for a 5:1 step-down transformer might be supplying 24 volts to power the control electronics for a heating and air conditioning device off of commonly available residential 120 volts 60 Hz AC. By simply adjusting the turns ratio of the transformer, a manufacturer could make this device available for a number of different primary voltage levels. Consider this same device necessitating a secondary output of 24 volts AC, however being operated at an increased primary voltage of 240 volts. Substituting in our given voltage values demonstrates this transformer would necessitate a 10:1 step-down transformer to achieve the same output voltage of 24 volts. Note the turns ratio doesn't mean the transformer literally has 10 turns on the primary and 1 turn on the secondary, but rather that the turns ratio is for every 10 turns in the primary, there'll be 1 turn in the secondary. Sticking with our earlier example in which the secondary possessed 60 turns, the primary for this 10:1 step-down transformer would have 10 times this many turns, or 600 turns. Makes sense. Alright, it's your turn. See if you can determine the turns ratio necessary to power the secondary winding with 24 volts AC, given a primary input of 208 volts. By all means, pause the lecture and try this on your own. If you're tracking, you should have obtained the following results. Given 208 volts is roughly 8.7 times higher than 24 volts, one might expect an 8.7:1 step-down transformer to fill the need. In keeping with our earlier example in which the secondary possessed 60 turns, the primary winding for this 8.7:1 step-down transformer would have 8.7 times this many turns, or 520 turns. Again, it makes sense. One might think a manufacturer wishing to supply 24 volts AC to some power electronics using 3 different primary voltage levels might necessitate 3 totally different transformers, each with their own specific turns ratio. One with a 10:1 ratio for 240 volt applications, one with an 8.7:1 turns ratio for 208 volt applications, and yet another one with a 5:1 turns ratio for 120 volt applications. However, a simple modification allows a single transformer to perform these different roles. Consider a multi-tap transformer, it being a transformer with different access points or taps on a single winding. For this particular application, consider a transformer with 600 turns in the primary. However, there exist taps or additional points of connection at 520 turns and another at 300 turns. If the secondary is assumed to have 60 turns, the entire 600 turn primary winding would provide a 10:1 turns ratio for 240 volt primary voltages. The 520 turn tap on the primary provides an 8.7:1 turns ratio for 208 volt applications, and finally, the 300 turn tap on the primary provides a 5:1 turns ratio for 120 volt applications. Thus, this single transformer with multiple taps in the primary is suitable for 240 volts, 208 volts, and 120 volt applications by changing a single point of connection. Granted, there's some extra weight involved with this particular transformer. However, the advantages of manufacturing this system using a single component suitable for export to multiple regions using different primary voltages, might outweigh this disadvantage. Transformers needn't always step down primary voltage. Consider a step-up transformer with a 1 to 50 turns ratio used to step up the 690-volt output produced by a wind turbine generator for delivery to the wind farm collector substation, which collects, hence the name, the output of the numerous turbines in the farm. In this occasion, a simple algebraic rearrangement of the turns ratio equation demonstrates the secondary voltage of this step-up transformer to be 34.5 kilovolts. Our output voltage would be 50 times our input, as we'd expect. Consider yet another application of a step-up transformer, in this case the collector substation, stepping up the incoming 34.5 kilovolts, yet again using a transformer with an output of 138 kilovolts for transmission to a distant city. See if you can determine the turns ratio necessary to power the secondary winding with 138 kilovolts using a primary input of 34.5 kilovolts. By all means, pause the lecture and try this on your own. If you're tracking, you should have obtained the following result. Given 138 kilovolts is 4 times higher than 34.5 kilovolts, one might expect a 1 to 4 step-up transformer to fill the needs. Again, it makes sense. Note the turns ratio is 1 to 4, correctly indicating that it is a step-up transformer and not a 4 to 1, incorrectly implying that this is a step-down transformer. The turns ratio is customarily expressed as the number of turns in the primary over the number of turns in the secondary, and not the other way around. Additionally, they're customarily expressed as ratios. Resist the temptation to simplify this to 0.25. Importantly, the turns ratio, primary to secondary, is directly proportional to voltage, primary to secondary. Before we move on, compare and contrast not only the step-down versus step-up relationship of these past example transformers, but also their larger roles. In the first scenario, we made use of a transformer to simply power the control electronics of some heating or air conditioning device, whereas the next series of examples dealt with transformers designed to transmit a massive amount of primary power from some distributed generation equipment to a city some distance away. In this sense, the first couple of examples might be referred to as control transformers, meaning a control transformer is designed to power low-power control electronics only, and not massive amounts of primary power. The second examples, in contrast, might be referred to as power transformer applications, meaning these transformers are designed to change the characteristics of massive amounts of primary power for transmission purposes. As one might expect, a control transformer would be a relatively lightweight, inexpensive affair, and a power transformer must be sufficiently robust to handle the amount of power being transferred. Don't for a moment equate step-up transformer with the term power transformer, because one needn't look any further than the transformer at the distant city being asked to step down the massive amount of power on the 138 kilovolt transmission line to a level more appropriate for distribution to their industrial and residential customers. The step-down transformer at the city would also be classified as a power transformer, since it's changing the electrical characteristics of massive amounts of power for the purposes of transmission. Other types of transformers exist, including, but not limited to, instrumentation transformers, distribution transformers, polyphase transformers, phase shift transformers, and much, much more. We'll examine these transformer applications in later lectures. For now, you should simply realize there exists a range of application-specific transformers, and not all transformers are directly interchangeable with one another.